VDI2035. My name's Alan Hart, and today we're going to do a video on water treatment in central heating systems, and we're going to look at the German standard of VDI2035. I've got Simon here with us today, and what we're going to do, on this system that we've got here, we're going to drain all this system down. We're going to fill it up with VDI quality water or demineralized water, and we're going to test it all. We're going to test it before, test it after. We've also got a slideshow at the end, and that slideshow will go into much more detail, and it'll show you step by step how to do VDI and what VDI is and what it means and what VDI is all about. I'll be totally honest with you, I've not worked to VDI in the past. I've always put chemicals into a system, so this today will be a learning curve for me, as well as hopefully you guys as well. Please, if you could put some comments below.
Hello, I'm Simon from Alexion. Alexion, we deal with products which meet the German VDI2035 standard. All our products are made in Germany via Electa, and today with Alan we're going to look at testing the water, filling the system, and basically looking at everything VDI2035. So before we start, we're going to take a water sample from the incoming mains. So this will identify what the incoming conductivity is, the pH, and we're going to have a look at what minerals are in the water. So we've taken our water sample, now we're going to get it tested. The reason I personally like VDI2035 is because we're working with specific parameters, and they're parameters that we can check on site, so we don't need to send off for any water samples. The test kit itself, the MP7, is very easy to use. So the test kit comes with the MP7 meter. So this will do the TDS, the conductivity, and the salts from the same probe. We can change the probes out and also check our pH. And then we've also got a simple drop test to test the total hardness. So if we get these parameters correct, we basically won't have any corrosion within our system. So it's very, very simple to monitor. Right, so we're going to test the water now from the sample we took outside. So I've put some water in the beaker from the test sample we took. I'm going to use the MP7 pen. Simply pull the cap off the bottom, and we're just going to turn it on. So the pen itself is going to test the conductivity, the TDS, and also the pH and your salts. So we're going to start off with the conductivity. So we're going to put it in, we're going to give it a little stir. So the incoming conductivity here is 193, so not particularly high, but still not within the limit of VDI, which is less than 100 microsiemens. And press the mode, and we've now switched to TDS. So this is measuring the total dissolvable solids, about 127. And one more time, switch to the salts, so about 90 parts per million there. So now we're going to test the pH. What I've done is I've just changed the water over in the test beaker so we don't have any contaminants. So very simply, just turn this anti-clockwise. I'm going to pull the probe out. We're going to get our new probe. So this one does the pH. So just on top we've got the little circuit board, and you'll see this is where we put the pins in. Untwist the base. Just be careful because there is some electrolyte fluid in there. Okay, so that just keeps the probe moist at all times. And we're going to simply line up the bottom with the pins. Push that in. And then tighten it up, and then we're good to go. So again, we'll just turn the device on. And the device itself will automatically recognise it's changed to pH. So we put the pen in, we're just going to give it a little stir. So we've got pH here of about 7.2, 7.24. VDI, realistically for this type of system that Alan's got, we want it near a 9, 8.5 and above. So now we're going to do the total hardness. So once again, I've changed the water, so no contaminants. So we're going to take the little test beaker and fill with 5 ml. So we're just going up to the line. So we've got some reaction agent here. So it's a very simple drop test. The first drop starts the process. I'm just going to give it a little shake in between. So what we want is it to turn green. So each drop from now on counts for 1 degrees hardness. So it's 1. 2. 3. That has changed. So that indicates 3 degrees hardness in German degrees. So now we've taken our water samples, and basically what we're going to do later on is we're going to fill Alan's system here with demineralised water, and what we can do is we can compare what we had before to what we had now. So you're probably wondering what all these tests means and why we're doing it. So there's a connection between the TDS and the conductivity. So essentially water is full of minerals, and then minerals have different charges. So there is actually small amounts of electric in water. So you have what's called your cations and your anions. Okay, so these charges are what basically give the water its electrical conductivity. So if we reduce our TDS, in a sense what we're going to do is reduce the amount of conductivity. So why are we reducing the conductivity? So we're doing that to stop galvanic corrosion. So galvanic corrosion is when you have a noble metal and a less noble metal. And what happens is the less noble metal transfers its electrons through the water. So the water is our reaction agent, it's our electrolyte, and it's passing its electrons to the more noble metal, which would be a cathode. And in doing so, what happens is the less noble metal, it basically gets attacked by any oxygen in the system. So if we have a low electrical conductivity, we're reducing our path for our electrons to move from one metal to another. So even in the presence of oxygen, having a low conductivity, we're essentially going to reduce our risk of corrosion within our system. So what we do is we reduce the mineral content, which reduces the conductivity, which essentially gives us a system where corrosion is going to be very unlikely. So we also, within our system, we tested the pH of the water. So the reason we do that is metals can essentially create their own covering. They're called oxide layers. These oxide layers allow the metals to protect themselves, so you get a very thin coating on the top of the metal. So what that does is, it's essentially like an inhibitor. It creates a false layer of protection. This is its own natural layer of protection. So different metals have different ideal pHs. For heating systems, typically we say about 8.5, because what that does is it will allow for aluminium as well. With aluminium systems, you don't really want pH above 9, but above 9 is quite good for stainless steel and iron and copper, etc. So as long as the pH is above or around about 8.5, we know our metals are going to protect themselves within the system. You can actually create an increased pH by boiling the system. So if you have an air separator on the system and you're boiling the water to above 60 degrees, it's called the self-alkalization zone. So what will happen is, as the water is heated, the gases are released, the carbon dioxide is released, and what will happen is the pH will naturally stabilise around 8.2, 8.5. It's something you'd want to monitor. It won't happen on the day you're there at the system. It might take a couple of weeks, it might take a couple of months. But VDI allows one full heating season for this to happen, because ultimately, if you fit a boiler in the summer, you might not be able to run the system for long enough for this process to happen while you're on site. But it will happen Luckily, using a device like the Clarimax, we actually leave the system after commissioning already around 8.2, 8.5, so we know the system's already at the state that we want it to be before we've left site. So what we're going to do now is we're going to take a water sample of Alan's current system water, and then we're going to compare it at the end to what the new system water is once we filled it with demineralised water. So when taking a water sample, what you want to do is you always want to run off a little bit of water first, and any stagnant water there. So it's got a bucket here. So run off the water, and what you want is a nice, slow, steady stream of water. There's our system water. So now we're just going to drain the system. Now we're going to take a look at the Clarimax itself. So the Clarimax is our demineralisation device. It consists of a cartridge. We use a mixed bed resin in our cartridge system. So we've got the housing itself, and then we've got the filter head. So it's a metal made in conjunction with Brita. So we've got the cartridge itself. So this is full of the mixed bed resin. It comes pre-packaged, so it's not a messy system to use. That simply fits inside. Got the little red cap. So this is a brand new cartridge. So every time you put the head on, just make sure the O-rings are in place and get wet at all. And then we've got the Clarimax head. So this head is what monitors the outgoing water. So it tells us with a very simple traffic light system whether we're in the requirements that meet the VDI filling standard. So very simply line up the lugs, push down, twist on, device turns itself on. If we hold this down for 5 seconds, hear the 3 beeps. This will constantly monitor now as we fill the system. So that's the device itself, as I said, designed and manufactured in Germany in conjunction with Brita. So we need to connect this to our system. Alan's got a Wiesen boiler here. It's got an internal filling loop. So what we've done is we've disconnected the internal filling loop, and we just fit some of our own fittings here so we can connect it to the Clarimax. The Clarimax has got 3/4 connections. These are obviously 1/2 inch. So we've got some little adapters here on little filling loop hose, and then we just utilise the little bend that comes with the boiler, and again put a little adapter on it, so we're ready to fill. So we're ready now to connect our hoses to the system. The Clarimax itself very simply tells you in and out. It's pretty simple. So you connect your inlet to the mains water, and then on this one it's the return, which will go to the outlet. Right, we've got our hoses connected now. We've simply utilised some fairly inexpensive washing machine hoses. They seem to work quite well. What we need to do the first time we use a cartridge is we need to bleed it from air and give the resin a rinse. We've got this little tube that comes with the device. I'm going to put that on here. Right, we've already got the water on this one. So we've already got a degree of water within the resin cartridge. There's a little handle on top. So what we want to do is we want to bleed this cartridge out. What we're going to do, we're going to fill the bucket up once, and that'll be fine. You don't have to do this every time you use the device. It's the first time you use the cartridge, you have to do it. My advice would be, every time you reconnect it, just a little bit, make sure we've got no air within there. So once the cartridge is bled, we're ready to fill the system. So you just fill the system like you would any normal system. So I'm just going to open up the other side of the filling loop here. Here the water starts going in the system. So the Clarimax computer at the moment has got one green LED. It's a new cartridge, this is what we expect. As I said, it's a very simple traffic light system. So green means we're good. Green goes up to about 35 microsiemens. And then you have the orange, which indicates amber, cartridge nearly expired. And then red, the cartridge has expired. So what we're going to do now is we're going to bleed the radiators and fill the system. So now we filled the system, what we're going to do is we're going to circulate the water a little bit, and we're going to make sure it's all fully mixed, and then take a water sample. So we've vented our system, we've run the pump. Now what we're going to do is we're going to take our sample. So remember, when you take a sample, you want to draw off some water first, make sure there's no stagnant water. So we're going to get rid of that. Then you want a nice steady flow of water. So now we're ready to test our water from before and afterwards. So before we do the testing, just going to show you how to disconnect the machine. It's always a good idea to depressurise it first. So the same way that we vented it before, we just open this, it's just going to remove all the pressure from within the cartridge itself. So when we take the hoses off, we're not going to get wet. So pressure's out of the system now, we're ready to disconnect the hoses. So now we're going to do our water testing. We've got our 3 samples here. So this was the system water. This is pure Clarimax water. And this is now our new system water. It's going to be quite interesting to see what the existing system water was like, because when it came out it looked pretty clear, but when you hold the two up there is a slight yellow tinge to it. Speaking to Alan, he actually did a video recently and he had some X800 running through these radiators, so this could be through some residue left from there, so it's going to be very interesting to see the difference in conductivity having the cleaner in there to the normal tap water. So we're going to do the existing system water first. So I've got my pen again, just going to put this in. So it's come out at 296 microsiemens. That's rather interesting because the tap water we tested originally was 198. So it's increased by 100 by having a bit of residue there from the cleaning agent. So it's really, really important to, when we're doing our testing, to make sure that we get all the system flushed properly and remove any chemical that we might have put in, because otherwise it is going to increase the conductivity, and what we want is a low conductivity. So it's really important to test before and test afterwards, and basically just test during your flushing. So just going to check what the TDS is. So the TDS is 195, and then I'm just going to check what the salts are. 138 parts per million. So what we're going to do now is going to change the probes and just check to see what the pH was. So we've got a very low pH here of 5.85. So from them test results, we can see that there clearly was some residue cleaner left in the system. Our pH had decreased and our conductivity had increased. So basically that's not what we want. We want a conductivity of less than 100 and our pH around 8.5. So what this basically stresses is when we're cleaning the systems, we need to make sure that any chemicals we use, we really do flush it out properly, and we check it as we're doing it. So we know once we start to treat the system that all the residue's gone and we're going to get the results that we require. So now I'm going to test the Clarimax water. So our conductivity here is 11 microsiemens. Our TDS has dropped to 7, 8. And our salts have dropped to 5 parts per million. So this is the water from the Clarimax. Change the probe over, we're just going to do the pH on the Clarimax. It's about 8.6. So that little test there just shows that the water that comes out of the Clarimax is already ideal for our heating systems. So when we're filling with the Clarimax, we know we're going to leave the system as we intend it to be. When filling the system, you want the system not 100% demineralised, you want a little bit of conductivity in there, so above 10, but certainly less than 100. Right, what we're going to do now is going to test the system water from Alan's system. So our conductivity now is 63 microsiemens. Our TDS has dropped to 41. And our salts are at 29. So we're now measuring the pH. and our pH is about 8.5, 8.6 again. So what this shows is that even though Alan's water looked okay and it looked relatively clear, that there clearly was some residue left in the system. So this is why it's important to check when we're flushing and when we're dosing our system that we're actually creating an environment where corrosion is not going to take place. Alan's systems now, because we filled it with the Clarimax, we've tested it, we've proved it, will meet the VDI2035 standard. So he's creating an environment where basically corrosion will be kept to an absolute minimum. So one of the questions Alan's been asked is, when we leave site, what happens if somebody takes a radiator off the wall and they dilute our system? Well, this is a problem for both chemical or demineralised systems. So what we have is an answer for this, and the solution is the PureFill Colour Guard. So it's a very simple device which has a little wall bracket, mounts on site, and you fill it in between the filling loop. So what happens is there's a colour resin inside. It's easy to monitor. It turns from blue to like a yellow sandy colour. When it turns yellow sandy colour, we know the resin's expired. So it's something that your customer can monitor very easily without the need for any kind of test equipment. So when the radiator comes off the wall and they go to refill the system, the water comes through, passes down through the resin and back out through the system, pre-treated and demineralised. Right, we have a short presentation here on what Alexion Water Treatment is as a company. We're going to go over how the demineralisation process works, also discuss our partners Electa, and just look at everything VDI. Electa are a German company, so Germany is obviously the home of the VDI. All our products are made in Germany and designed by Electa. Since 1991, Electa has been leading the way in chemical-free water treatment, offering products for heating water with a view to protect against damage caused by lime, corrosion in heating systems. High-quality system water is produced thanks to precision German engineering. All core products are designed and manufactured via Electa in Germany, the home of the VDI2035 standard. High purity water with proven protection against water-sized damage is created with the greatest possible avoidance of chemical additives for water conditioning. Compliance with guidelines such as water treatment according to VDI2035 and others. Improvement of the environment balanced through reduced use of chemicals with cost savings due to functional, low maintenance water filter systems. With a focus on water treatment, we have been dealing with electrochemical water treatment processes for over 25 years. This experience allows for an ecological, economical and sensible approach against water-side damage with domestic, commercial and industrial heating and cooling systems. What is a VDI2035? The VDI2035s are guidelines set by the Association of German Engineers. It is an organisation with over 150,000 engineers and natural scientists. More than 12,000 honorary experts process the latest findings every year to promote the technology location. Established in 1856, the VDI is today the largest engineering association in Western Europe. The VDI is not a union, and the association promotes the advancement of technologies and represents the interests of engineers and engineering businesses in Germany. VDI2035 Part 1 refers to prevention of damage in water heating installations, scale formation in drinking water and heating installations. VDI2035 Part 2 refers to the prevention of damage in water heating installations, waterside corrosion. There also is a VDI Part 3, but that refers to the corrosion which is caused by gases in gas carrying systems. VDI2035 is a preferred method of many of the world's leading manufacturers of HVAC equipment. In Germany, Electa supports the likes of Caleffi, Romea, Solvis, Rotex, Zander and Dimplex, amongst others. Quick look at the Clarimax here. Water supplied to the grid contains undesirable salts, minerals and gases in which contribute to corrosion within the heating system. VDI2035 stipulates that the total hardness and the conductivity of the heating water does not exceed certain levels, which can either be achieved by pre-filling the fill or by treating the recirculating heating water. Using a resin-based system, during the demineralisation process, corrosion-promoting ingredients such as chlorides, sulfates and nitrates are removed from the water. Based on a unique composition of different ion exchange resins, our mobile or permanent filling devices offer reliable desalination and provides heating water with a low electrical conductivity in the range of 0.1 to 100 microsiemens and a total hardness of less than 0.01 German degrees. A special plus when using the Clarimax is it will typically provide a pH of around 8.2 to 8.5. What we have here is a table which shows what we're looking for in terms of total hardness. The VDI2035 is currently being updated, so we have the existing one here and also the latest edition. What is the total hardness in water? We've got two tables here, they're together, we've got the cations and the anions. So these are what we typically find in our water. Interestingly enough, the total hardness refers to the calcium and the magnesium. So total hardness and limestone formation. Carbon dioxide keeps calcium in solution. When heated above 60 degrees or reduced pressure, carbonic acid escapes. Lime participates. So the consequences of having lime in our system is we get limestone scaling, which causes boiling noises, change of flow conditions, damage to moving parts, and loss of heat transfer. 1 millimetre of limestone layer can equal less than 10% energy efficiency reduction. We've got some blockages here, erosion and stress fractures also shown. The 2035 directive is very simple to follow. This table here shows what we're looking for in terms of pH, electrical conductivity, chloride and sulfates within our system. If we achieve these, we will create an environment where corrosion cannot take place. What does this all bit mean? It's long been proven that reducing the conductivity reduces the risk of corrosion. Removing the minerals stops the formation of scale. It is possible for metals in the system to create their own natural oxide levels to protect against corrosion, even in the presence of oxygen. To do this, we need stable pH of between 8.2 and 9 for systems with aluminium. Having a stable pH within the limits set via VDI 2035 will allow the metals to be passive, protecting themselves without the need for chemical additives. What influences the electrical conductivity and the pH value? The table here shows that we've got cations and anions. These are our minerals within the water. They have different charges, so the minerals are what give us our electrical conductivity. By removing these minerals, we reduce the conductivity because we've got rid of the positive and the negative charges. Influence of electrical conductivity. This graph indicates the range where the amount of oxygen that we can withstand within our system. The lower the conductivity, the more oxygen we can withstand within our systems, and essentially we can stop corrosion happening at the surfaces of the metals. Looking at the pH value, why they're important, having the correct pH value allows the metals within the system to become passive. When they become passive, they're creating their own oxide level at the surface. This surface layer protects against corrosion, even in the presence of oxygen. Our table here shows the ideal pH range for different metals. As you can see, they're all different. As a rule of thumb, we're looking for about 8.5 because it's good for aluminium, it's good for all the metals within the system. As a rule of thumb, if we're around 8.5, that's what we're looking for. These little test jars, they're just showing that you can have the correct pH, but if the conductivity is too high, you still will get corrosion. We really need to be looking at the system as a whole and making sure that all our parameters are correct. Look into some basic science. A water molecule consists of 3 atoms, an oxygen atom and 2 hydrogen atoms, which are bonded together like little magnets. The atoms consist of matter that has a nucleus in the centre. Water consists of both positive and negatively charged ions. Corrosion is an electrochemical process which relies on water to be the conductor. It's our electrolyte. Pure water is a poor conductor of electricity, and only water rich in minerals acts as a good conductor. Reducing the conductivity in water prevents galvanic corrosion, where electrons are passed from different metals. Here we have our galvanic series chart, and as you can see, the metals are listed in order. We have our what would be classed as anodes at the top and the cathodes at the bottom. So this shows about where metals will pass different electrons from one metal to another, depending on how noble it is within this series chart. This is important to stop galvanic corrosion. So taking a look at waterside corrosion, what we've got here, we've got our cations and anions. So these are the minerals that we will find in our water. You'll see that some are positively charged and some are negatively charged. They're all balanced. Deionization is a physical process which uses specially manufactured ion exchange resin. The majority of water impurities are dissolved salts, and the deionization process produces a high purity water. Minerals and salts are found in regular tap water. These minerals are what give the water its electrical conductivity. These different minerals carry either a positive or a negative charge. The positive charged minerals are attracted to the cation resin beads, where they are swapped to positive hydrogen electrons. The negative charged minerals are attracted to the anion resin beads, where they are swapped with negative hydroxy electrons. Right, so what we have here is the cation beads and the anion beads. We've taken sodium chloride as an example. So the sodium is positive, so it's going to get attracted to the cation bead, and the chloride is negative, so it's going to get attracted to the anion bead. They swap places, and essentially what we're going to get is pure H2O. So resin is made up of polymer beads. The polymer beads have different charges, and this is what attracts the different ions within the water. Filling water treatment through demineralization. Two types of resin are required: resin loaded with hydrogen and hydroxide ions. Positively charged ions are exchanged with hydrogen ions, and negative charged ions are exchanged with hydroxide ions. A couple of charts here to show different levels of different water quality: hard water, completely demineralized water, and soft water. Got some water mixtures here. As I said in our video, you don't want 100% demineralized water. It needs to be above 10 microsiemens, but less than 100. Rule of thumb, you're looking at 80-20% mixture. Mixed bed resin. Ion exchange resins are widely used in different separation, purification, and decontamination processes. The most common example are water softening and water purification. Ion exchange resins or ion exchange polymer is a resin or a polymer that acts as a medium for ion exchange. It is insoluble matrix or support structure, normally in the form of small microbeads. These beads are usually white or yellowish, fabricated from organic polymer substrate. So we're going to take a look at the Clarimax here. So the Clarimax itself is made from metal. It's made by Electa in conjunction with Brita. You have the expansion medium pre-filter at the top. We've got the mixed bed resin, and we have a fine filter at the base of it. We've got the German electronics at the top, which monitors our system fill and the quality of the water that we're putting into the system. So on this in the video, self-alkalization usually takes, we allow up to a whole heating season for it to happen. Using the Clarimax, we can actually get this to happen instantly, and we've demonstrated it in the video. Using the cartridge-based system, we're going to get a pH of about 8.2, 8.5 straight out the cartridge, so ideal for our heating systems. We don't have to wait, we don't have to go back and retest, we're there already. We've got accurate monitoring using the Clarimax. It's German engineering, it's German electronics, it works really, really well, it's really, really accurate, and it's easy to follow. We have the traffic light system, so we've got green, yellow and red. Green means we're within the limits we want. Orange, the resin's starting to expire. Red, we're no longer in the VDI requirements anymore, so we need to change our cartridge. The information on the Clarimax here, so it was designed and manufactured in Germany, made in collaboration with Brita. Accurate German electrics with easy to read traffic light display, metal body for long lasting life. Is suitable for inline treatment or system top-ups. Maximum working pressure just under 7 bar, maximum temperature 60 degrees. It's user-friendly with self-sealing O-rings and can be opened by pressing a simple button, and it's a really simple twist mechanism we're using. A really good bit about Clarimax is the water doesn't actually go inside it. Everything is withheld within the cartridge itself. A few brief slides here on system filling. We've done a system fill with Alan here today. We need to complete a hot and cold flush. We need to make sure we've removed any flux, grease, existing paste, any chemical cleaners, we need to making sure we get all them out beforehand. We need to test it. We need to make sure that the water is of the same quality as the incoming main. We connect the Clarimax in place of where the filling loop would go. We fill the system. Again, we're looking for about an 80% demineralisation and 20% normal water to make sure that we're not at 100% demineralised water. We need to be above 10 microsiemens, but less than 100. After that, guys, you just fill the system as normal, go around venting it, circulate it, test it. We know we're there. Inline conditioning. To do this, we need to monitor what our incoming is. We have a little meter to do this, the combination meter. It will tell you what your incoming is, and it will also monitor how many litres we've treated and go into the system. So this is available as an optional extra. It's not necessary for standard filling, but if you want to be able to monitor your inlet, what it is, or the amount of litres you're putting in the system, then it's required. During inline treatment, you don't want to be putting strong chemicals through the device itself. It's not good for the resin. It's going to reduce the life expectancy of the resin also, and you don't want dirty water going around it. So make sure the system's clean. If you've got any doubt, we do optional filters which can be fitted on the inlet. There's lots of different ways to connect this to the system. You can either use like a flushing bypass. Many manufacturers now with filters have their own adapters. You can get pump adapters, so it's quite flexible. It's quite easy to do. You may or may not need an additional pump. Depends on what pressure your pump in the system can generate. The Clarimax itself has a non-return valve built in there, so it needs to lift that, and also some flow restrictors. The Clarimax are allowed up to 8 litres per minute inline treatment. Inline conditioning. So we might want to do inline conditioning when we've got an existing system. We want to improve the water quality of an existing system. It might not be preferable to drain and refill this system, or you might have an underfloor heating system. It's particularly good for underfloor heating systems. You don't need to dump the water that's already in the loops. It could be quite hard to get rid of them. The same process applies, as in you need to clean the system, you need to make sure that our water within the system's not got heavily dosed with chemicals. We've got a good base to start with, and essentially what we're going to do is we're going to use either a separate pump or the system pump, if it can create enough flow and the pressure to circulate the existing water around the system through the Clarimax and back out. We can monitor what's going into the Clarimax by using the combo meter. It also registers the amount of litres we've used, and then the outgoing, we just use a simple traffic light system on the front of the Clarimax itself. Inline treatment. This technique may be preferable for installations where you want to treat the existing system water, improve existing quality for ease of systems such as underfloor heating, where the loops have been filled and pressure tested with raw water. Complete the flushing and commissioning of the Clarimax as we've done in the video. Connection of the Clarimax can either be done using a flushing bypass, a flushing adapter for your air, dirt or magnetic filter, or even a pump adapter. Make sure you have the hoses connected the right way around. A separate pump may be required to generate a maximum amount of flow around the Clarimax due to the non-return valve and flow restrictor within the device. Turn on the Clarimax monitoring system. The system is ready to be treated. Make sure all the zones in your system are calling for heat. Turn the boiler stat down to minimise its setting. The boiler system pump will now operate. As the system will never reach the desired temperature due to the boiler stat being set to a minimum, the pump will run continuously. Monitor the traffic light display on the Clarimax and the BS7593 meter on the inlet to ensure the fill water meets the correct standard and the resin has not expired. The controller is everything. We need to make sure that we're checking our water on our services. So regular water sampling to avoid errors, annual check of the pH, electrical conductivity and total hardness. If you have any doubt, send the sample to a lab. Always take in a good place where we've got steady flow of water. Rinse the delivery nozzle to avoid any stagnation. Use suitable plastic containers. Fill the container completely, and make sure when you take the sample you're letting the water run in slow, steady stream. Now we're going to complete our drop test to do our total hardness. we need to fill the small test beaker with 5 millilitres of water. 1 drop of the reaction agent to start the process. We need to shake the tube until it turns red. We're now going to add 1 drop of reaction agent and shake. Every 1 drop counts for 1 German degrees in hardness. We're going to drop and count and shake in between until the solution turns from red to green. The number of drops indicates how hard our water is. Interpretation of the results. This discoloration is very weak at the beginning. This is normal and is more pronounced when there is a high salt content in the water. The discoloration is immediately green at the beginning. In this case, the total hardness is at a level of less than 1 German degrees. The first drop already counts. The first drop is used to compensate for the hardness, less than 1 German degrees. The following drops count as 1 German degree. The heating water is coloured red or black. Does the test work? This is only possible in approximately clear water. If there is strong discoloration, a total hardness test must be carried out by a laboratory. Test kit MP7. Install measuring electrode for electrical conductivity. Switch on the device and make sure the display shows the microsiemens sign. Otherwise, use the mode button to select microsiemens. Take a new water sample for each test. Contamination in the vessel can falsify the sample. Leave time. Wait until the temperature is stabilised. Remove air bubbles from the sensor by tapping lightly on the container wall. Read the value. When the temperature is stabilised, read the value. Consider the tolerance of plus or minus 10%. This chart here is basically going to show us our interpretation of the results regarding electrical conductivity. So as you can see, it will tell you thumbs up if we're in the zone and thumbs down if we're out of the zone, and basically what we need to do to try and rectify our system. Using the MP7 test kit for measurement of pH, the electrode for the pH must always be stored in a transparent protective cap. The pH electrolyte, which is potassium chloride, must always be present in the protective cap, never another liquid. Always rinse the electrode after use and then screw on the protective cap back on. Measuring the electrode for pH value, unscrew the protective cap before measuring and rinse your electrode with water, then immerse in the sample. Wait until the temperature is stabilised, remove the air bubbles from the sensor by tapping lightly on the container wall. We then need to read the values. When the temperature is stabilised, read the value, consider a tolerance of plus or minus 10%. Interpretation of the pH results. This table shows us where we need to be regarding our pH levels within our system. It gives a breakdown of the different metals and where we need to be. Thumbs up is obviously good, thumbs down, we're out of the zone and the requirements of the VDI2035. So we've got the Clarimax Bambini here. The Bambini is the Clarimax little brother. It's a good starter kit for anybody who's looking to fill with demineralised water. It's very affordable. Got some other accessories. We've obviously got the MP7 test kit, we've got flush and bypass, system filter and also a hose kit. With equipment becoming ever increasingly more efficient, it has never been more important to get the system water quality correct. Gone are the days of large waterways and energy wastage. With these changes in design, the margin for error has greatly been reduced. The water is the largest component of any heating system. Treat it well. To get in contact with Alexion Water Treatment, you can reach us via email info@alexion.uk, our website www.alexion.uk. We have a LinkedIn page and also our Twitter page @Alexion_UK.
Thank you very much for that, Simon. Very, very interesting indeed. And to be honest, I've learned a lot from you today. So yeah, thank you very much. As I say, please put some comments below. Tell me what you think. Tell me if you've learned out from this video. And yeah, thank you.
So our conductivity now is 63 microsiemens. Our TDS has dropped to 41. And our salts are at 29. So we're now measuring the pH. And our pH is about 8.5, 8.6 again.